So yeah, if we think about, so we'll try and do that theoretically real quickly. What we're looking at for this exam, okay? We're looking at kind of, well, actually I'm gonna take away dipole moments. We're looking at our bond types or our bond classifications, which is kind of a nasty one because there's a couple different classification systems we could look at. The classification systems that we did in Unit 1 were sigma versus pi, and that was kind of just the recognition behind where those are coming from. What we're talking about for bond classifications here is our nonpolar covalent, our polar covalent, and our ionic bond types. Once we have those bond types, that's where we can get into some nuances of kind of repercussions of them, and that's where we get dipole moments. That's dealing with our partial charges, our partial positives, and partial negatives. Okay, that's where that content comes from. Once we have that content, we can then start to talk about what that means when you bring those molecules near each other, and that's where we expound into our forces. Okay, so our forces being ionic, that's an I, hydrogen bonding, dipole, and our London dispersion forces. Okay. Once we have those forces, we then have to look at their applications of them, and that's where we see melting points, boiling points, which ultimately I would put all together, solubility, right? And that's what's happening out of those forces. Once we know the forces, we can then extrapolate out to what those things mean. Okay? After we get forces, kind of the tail end of that gets us to reactions. So when we start talking about reactions, we have to understand what reactions are, what they mean, and all of that. And so where I would kind of took it was a brief overview of kind of our reaction pieces, is how I would call it. Okay, so our reaction pieces, this is our energy diagrams. This is dealing with the concept of equilibrium a little bit. Okay, we didn't introduce the terms exo or endothermic, but ultimately those are references of relative energies of our reactants versus our products. Trying to write it clearly and clearly screwed that up. Our reactants and products. Also bring in the concept of our activation energy for a reaction to go, which is looking at the relationship between our reactants and our transition state, which is the peak on an energy diagram. So if we're looking at an energy diagram, we've got something like this. We usually show the transition state as a double dagger. Okay? We've got our reactants and we've got our products. We'll make reference to those periodically. Really all I want you to be able to do is pick off relative energetic differences between those. Okay? Once we have kind of our reaction pieces, now it's, well, how can we actually use that information into different types of reactions? Okay? And in particular, where we started was our acids and bases. The acids and bases, theoretically, as an overarching concept, was supposed to be a review. So we get our raw definitions. Okay? The definitions being, I don't know why I'm changing the color, but I'm going to change the color. Our Bronsted-Lowry and our Lewis definitions. Our summary was that Lewis wasn't useful, and we instead switched to nucleophile electrophile chemistry, which then also simplified and meant we didn't have to reference Bronsted-Lowry anymore. We could just call it acid or base. Right? So those core definitions were now applied for us. Right? What we then went through is specifically what happens in those reactions. Right? And so when we look at those reactions, we could now start to predict products. We can predict products of our acids and bases because we know the definitions of our acids and bases. So that's something that we're trying to use our old content knowledge to kind of help out. Okay, so we can predict products from these. Okay, we can predict the directionality of a reaction. right? The directionality of the reaction is exactly what you were asking about, is tied back to pKa's, okay, if we want to try memorization. We will very quickly find that you aren't going to be able to memorize all the pKa's of everything thrown out there. And so you need some other system to rank those. And that's looking at our reactivity rankings. I'm trying to remember what exactly I call it. Okay. This is a really, really critical, important aspect to nail down. This is where we look at charge, size, electronegativity, resonance, induction, and we really hope we don't have to actually get out into that category because things get really challenging out there. Okay. Within those reactivity rankings, one thing that did fall, well, not fall out of it, but was part of that, was looking at cation stabilities. Okay. And relevant to our acids and bases would be our anion stabilities. And we'll go through and look at some examples on that. Okay, so when we go through to look at acid-base reactions, we want to be able to predict these products. And actually, I forgot, back with our reactions, we also have curved arrows. So same concept as resonance when we're talking about our curved arrows, but now we're making and breaking sigma bonds. So there's a change in kind of the dynamic of how we use those arrows. The last piece, okay, is now kind of the overarching view of what can we do with all of these things. And this is what I would call the elementary mechanistic steps. Okay, and at the same time we could throw reactions in there. So I want you to be able to look at a reaction and say, that is an acid-base reaction. That is an elimination reaction. That is an addition reaction. I want you to just be able to identify the key characteristics of those reaction types. Okay? Taking it a next step, the reaction types don't show anything about how the reaction works. There's no curved arrows. Okay? Where the curved arrows show up are now mechanisms, how the reaction happens. Okay? And sometimes we will eventually get into the why those reactions happen. Okay? That why is ultimately pushing back to our reactivity rankings and cation stabilities and all of those kind of reaction things. So that elementary mechanistic step part is, I just want you to be able to, again, look at a mechanism and say, this is what it does. This is the type of mechanism that's happening here, so that you could be able to predict that occurrence. So that's not too bad. In 8 minutes, I think we summarized everything that's going to happen on our exam. Okay? And if that looks daunting, it should. There's a lot of pieces here. Okay? All of this stuff relies heavily on Unit 1. What are our structure interpretations? So we have to still hold that content, how we manipulate and think about our structures and our drawings. But now what we're doing is layering in this extra information of how those things can change around and how they can interact within their environment. Okay? That's a pretty big jump. Okay? Kind of makes sense? Okay. To your question of figuring out what's going on within our acid and base reactions. Okay, before I do the next move, because the next move is delete the screen. Am I good to delete?
Can I take a picture?
Yes, absolutely.
It's just easier than
Yep.
screenshotting from that.
Yep.
Thank you.
And I will say it is recorded, it should show up, but yeah, you're absolutely welcome to take pictures anytime.
It's just sometimes I'll screenshot it and sometimes it's
Blurry.
Yeah, pixelated.
Yeah. Okay, so we picked the classic reaction before was looking at benzoic acid. Again, I'm sloppily drawing it here because I'm not going to keep it. Okay, so we looked at benzoic acid and we tried to figure out what was going on with it. Okay, what we're going to switch to now is not benzoic acid. Let's pick something that's entirely different. Let's go through and pick what structure do I want? Let's go with something that's actually a little bit, well, benzoic acid is actually relevant for y'all. Let's pick the amine functional group. we're actually gonna do a couple things with it, I think. Right? And we wanna predict something about its reactivity. What do I wanna react it with? Yeah, we'll react it with two options. So in this particular case, I'm gonna shift and move this. And by shift and movement, I'm gonna erase everything. The question was really talking about our acids and our bases. So before we get into our acids and bases, let's make sure we know what our definitions are. What is an acid?
Hydrogen.
Okay. So, I'm trying to write what you guys mentioned. Okay. I heard donate hydrogen and I heard donate proton. Okay. Officially, hydrogen and proton are different things. If we look at a hydrogen atom is a proton and an electron. That would be the Lewis structure for a hydrogen atom. Okay. When we say proton, are we saying the subatomic proton?
Yes. No.
No, we're not saying the subatomic proton, and that becomes one of the confusions. Okay? What we're referencing is, again, the hydrogen atom, but the hydrogen atom that is missing an electron. Because it's missing an electron, its overall charge is positive. So when we talk about acids, we're talking about the donation of a hydrogen ion. So if you say hydrogen ion, fully on board. If you say hydrogen, that's vague. I don't know exactly what you're referring to.
Hydrogen proton.
Okay? And then why can we call it a proton?
Because it's positive.
Nope. Because if we run a reaction with lithium, lithium ion would also be positive, but we're not going to talk about it as a proton.
Is it because there's two electrons?
Nope.
Well, there's
Define hydrogen. Which sounds like a really weird question for you all, probably because none of you had me in Gen Chem and Chem 130. That's one of the things that I ask students to do. Define the element.
Like an atom, a proton.
Define.
the atomic
Are there? Okay. What are the things that make it? That's our definition. So if we look at a hydrogen atom, what does a hydrogen atom have? What defines it?
Choose hydrogen.
What is hydrogen?
An atom.
What makes an atom?
Protons.
Okay, so protons, neutrons, and electrons. All of those things make a hydrogen?
It's just one proton.
Hydrogen, by definition, is one proton. If I add another proton, it is no longer hydrogen. It's helium. Okay? How many neutrons does hydrogen have? Zero. Harder question. How do you know that?
1 plus 0 equal 1. It needs to be both of them plus need to be the one proton.
I don't know what that means. You might be right, and then we just may be hitting a language. And that language barrier, in fairness, is everybody, not just you. Like, it's hard to go through and explain that. So you're saying the protons plus the neutrons must equal 1.
Its atomic number? Is that what you're trying to say?
It's not its atomic number, though. Right path. So, and I think you're on the right track. You're just not using the right words. And there comes the problem. There's lots of words to describe what happens with an atom.
Mass?
And with an atom, hydrogen, the atomic number is the number of protons. What we want is
The mass.
the mass.
Atomic mass.
And the atomic mass for hydrogen is
1.
1. And we would see that on our periodic table that we conveniently don't have in this classroom. But if you look up the atomic mass for hydrogen, it's 1.00192 whatever. It's 1. Okay? Which means it only has 1 unit, if you will, of mass. Well, what do we know about protons? They have a mass. A mass of what? 1. What do we know about neutrons?
0.
They don't have a mass, or they don't contribute.
Neutrons have a mass of 1.
There's just
So how do we know we have no neutrons? The mass for hydrogen was 1. If I had a neutron, that would be a mass of
2.
2. Okay? So if we're looking at what defines hydrogen, it's a proton with no neutrons. How many electrons should it have?
1.
Awesome. This is what we would define as a hydrogen atom. 1 proton, neutron, or 0 neutrons and 1 electron. Okay, that is a hydrogen atom. If we're talking about your definition for acids donating protons, what are we talking about? Well, we're talking about H+. How do I become a positively charged hydrogen? I have to lose that 1 electron. And if I lose that 1 electron, what's left?
1 proton.
1 proton. Okay? And so in that question I asked you, are you talking about the subatomic particles? We want to say no, because when we're talking about the subatomic particles, you're now talking about nuclear chemistry. I'm reaching into carbon and I'm ripping out a proton out of the carbon atom. That's not at all what's happening. Okay? What I'm doing is taking a proton, the hydrogen identity, that's chilling outside the other atom. It's its own identity. And I'm now saying you need to chill out over here. Okay? So we're not doing nuclear chemistry. What we're talking about moving is this thing that we call hydrogen that we can also conveniently call a proton, just because that's all that makes it up. Okay? So I can do this. This is a horrible example, but whatever. If I rip away a proton, what's left? Well, the hydrogen doesn't have any of the electrons, which means those electrons had to then be left on the carbon, which is why we get the lone pair, the negative charge. Okay? If we talk about this as nuclear chemistry, and we rip away a proton from this molecule, what we might get is this. Okay? What happens when I take a carbon, a proton away from carbon? I becomes a different element. The identity of the element changes. We're not changing the identity of elements. Okay? All we're changing is the electron balance around them. Okay? So it's something we want to be careful with. In theory, it's not a mistake that you would make, because the odds we would change the element if we did that on a multiple choice exam, you'd be like, why are you doing that? That's dumb. I'm not going to select that answer. Okay? So you would already have kind of a reflex to not do that. Okay? But I want to make sure we're clear what we're talking about. Okay? So this would be a hydrogen ion, okay, or a proton. So what then must be a base? Okay? And we can use language of a received. You can tell how much I don't like that word. Received a proton, or a receiver of protons. Okay? So when I tend to talk through them, you will hear very consistently the same ultimate kind of definitions. We're looking at a proton donor, and we're looking at a proton acceptor. Are those definitions different at all? No. They all have the exact same intent. They're describing what's going on behind it. It's just what word choice we choose to run with. Okay? For consistency's sake, I try to match the exact same thing, because it also then works for nucleophiles and electrophiles, and it's a subtle change in the language there. Okay? So cool. We can now go back to the example we wanted to do. Would I expect this molecule to act as an acid or as a base? Okay? And we got exactly what I wanted to hear. One person said acid, one person said base. So we're 50-50. What does that mean? We don't know. So what should we do? Yeah. Let's try both. Okay? So what we would try and go through and do is predict which way we think this is going to act, okay, preferentially. And that's where this one becomes particularly dangerous for us to work with, okay, but we'll play through it and see what happens. Okay? If we're going to say it acted as a base versus our acid, we okay with that? Okay, if it's going to act as a base, what does it need to react with? It acts as a base. What should it react with?
Oxygen.
Acid.
An acid. Keep it simple. Okay. Now that we know it needs to be an acid, do we know any acids?
Sodium.
Hydrochloric acid.
Okay. I'm going to come back to you in a second. So hold what was in your head because you're wrong question. Okay. What did you suggest?
Hydrochloric acid.
Hydrochloric acid. Okay. So, and based off of some interactions with people, people are, oh, I got to predict reaction. You don't have to predict most reactions. The only reaction you need to be able to predict is acid-base reactions. That's all you have to predict for this unit. Okay? So if we go through and run this, we know the acid must donate a proton and the base must accept a proton. Okay? So what changes in our structure? So where's your focus? Do you want to look at the nitrogen compound or do you want to look at the HCl compound?
HCl.
Okay? If it acts as an acid, what must happen to it?
Donates the nitrogen atom.
Okay? Which means if I look at what happened, that's past that reaction arrow, what should I draw?
An arrow.
I don't need it. So arrows are the right idea. That's describing what's happening here. We don't even need that yet. I didn't ask for that. All we're relying on is that HCl is an acid. It needs to donate a proton. Okay, so if what I'm asking here is, here's me, right? Ta-da, me, holding onto a pen. Okay, I'm a pen donor. What would I look like after I've donated the pen? No pen. Okay, so I draw nothing. When I donate this pen, all of a sudden, poof, I'm gone.
The pen.
Separate.
You can, okay, you can see me still. I'm still there. So the pen can't be attached to me anymore. So what would I have to draw?
The chlorine by itself.
I would have to draw me by itself. We revert this back to the HCl. What do I need to draw? The chlorine by itself. The chlorine should not be holding on to that hydrogen anymore. So I would need to draw that chlorine. Okay? And those three lone pairs, because those didn't do anything. All we were talking about was the hydrogen. Okay? But now we got to be a little bit careful. The hydrogen was connected to the chlorine through that bond. Okay? The hydrogen came off as what?
Proton.
H plus, which means how many electrons does it have?
None.
None, which means where did those electrons go?
Back.
Chlorine.
They're on the chlorine, which means what I should be drawing on that chlorine would be,
An arrow from the bond.
we'll come back to that. Okay? I still don't even need arrows, okay? And I love the arrows. Arrows are great. Okay, but all we're trying to do is just push raw definitions. Okay? What can we get through if I have the raw definition? Okay? And I heard a bunch of people say, well, shouldn't I also draw the pen? Yes, but I have to know what else to draw with the pen. Okay? So just drawing the pen over here, does that mean I donated the pen to anybody? Okay? Like, I can file all my taxes. I donated $5 because I set $5 down inside my house. It's no longer attached to me, right? So that means I donated $5? No, it doesn't work like that. I have to say where that went. I have to explain that. So what did I donate that pen to?
To your base.
Okay. Let's pretend those are the same thing. To some amorphous blob in our drawing up above. Okay. In this particular case, it had to donate it to the base. Okay. So what happens to the base when a reaction happens? Well, the amorphous blob is still there. It didn't change. It's still present. So I should redraw that. But it must now also have one hydrogen. Well, now the question becomes, where do I place that hydrogen?
Above nitrogen?
Why do you want to attach it to the nitrogen?
Because it has the lone pair.
Okay. If we're now thinking about how our reactions work, that positive thing can't attach to the base unless there's electrons there to make the bond. So if we go through and look at the rest of the structure, we do have electrons, but those electrons are already occupied in bonds, which means they can't share those electrons out to make that hydrogen. The only place we could do that would be that lone pair of electrons. That lone pair of electrons is what's going to share to form the bond with the hydrogen, which means what happens to the lone pair? I can't draw it again. I have to draw it as a line. Okay? Do I now have complete final drawings?
No.
Okay? I have to remember all the way back in Unit 1 that when I have chlorine with no bonds and 4 pairs of electrons around it, that it is negatively charged. Or I calculate formal charge. I have to. Okay? Now am I done? No. What else is wrong? I'm whispering so people turn up the volume in the video.
And then you're gonna be really loud.
Yeah. I won't do that.
Do you
That's
want, like, labels on things? Like,
Labels are an awesome idea. We will come back to that. We've actually already established some labels, so I'll go back through and write those in. These are acids. This was base.
But, like, would you want us to do that if it was?
Is it a question that can be asked? Yes, and so we'll lean into that. But first, we've got to fix our drawing because the drawing is wrong. Chlorine is lovely.
Is it your nitrogen's charge?
Something with my nitrogen is problematic. My nitrogen is
It's negative?
it's positive. Okay. How do we go through and do that? Well, back in Unit 1, you were told to memorize certain common bonding patterns. And if you chose not to memorize them, then you should have done a bunch of practice so that you would get used to it, so that when it shows up like this, you don't have to calculate formal charge. You don't have to do all those other things. It's boom, I know nitrogen's positive because it's got 4 bonds. That's where it is. Okay? I fully acknowledge we don't have a lot of time, and it's a new relationship. You don't know how much to trust me telling you it's important. Sorry. I'm telling you it's important. Okay? So now our structures are good. I'm happy with those structures. Okay? What else could we go through and do? Sydney's suggested like 4 different things. That's an exaggeration. I think it's only been 2. So
Like labeling things?
cool. So we could go through and label the results of these. Okay? That labeling can become a little bit challenging because we've got to figure out what's going on within it. And most students seem to struggle with labeling products because, well, they're products. They're like I told, they don't react. Except, what's the one really big piece that we have to remember with chemistry?
No reaction is still a reaction.
They're reversible, not necessarily no reaction. What no reaction means is that the reverse reaction was more likely than the forward reaction. So that these reactions are reversible, which means when we get to the products, they are also reactants and they can progress backwards. Which means if we ran an acid-base reaction forwards, guess what's going to happen when we run it in reverse? Also acid-base. So you should be able to label acids and bases on the product side.
Acid,
What are you pointing at?
base,
So you're pointing at the chlorine
Oh,
to be
wait.
an acid?
the switch. So then this becomes your acid and this becomes your chlorine becomes your base.
Okay. So what kind of question do you think you would get me asking?
To explain why,
Uh-huh.
because in this scenario, when you run it backwards, the nitrogen is now gonna donate one of its hydrogens.
So when we go backwards, one of our options, those pictures up top are kind of bugging me. I want to be able to point. When we go backwards, we're going from here over to here. And what changed in that structure?
The hydrogen,
It no longer has a hydrogen. Why? Because it donated it to something else. And if it is now a hydrogen donor, it must be
an acid.
an acid.
Can't you just do with, like, so going back to your original question of which one's the acid and which one's the base.
Yes.
Or is it an acid or a base? Technically both, depending on which way you're running the reaction. Because over here, we ran it as a base. Over here, it's an acid. So like if you just gave us that structure, even without like the hydrochloric acid, how would we know if it's an acid or a base?
Okay, so the how we know whether it's an acid or a base is what we're actually setting out to run. Okay, that was our option here. And so that's an awesome question. But where I feel you're asking that is you're saying, I didn't think it was coming back. You're saying this structure acted as an acid. So isn't this one acting as an acid and a base? No, this one is only acting as a base. This structure is acting as an acid. They're related to each other, they're tied. But once this has donated its hydrogen, accepted its hydrogen, it is now a new structure. It's an entirely new compound, and the chemistry of this is vastly different than the chemistry of this. Why? I changed the bonding pattern. It's a different molecule. Okay? Entirely different outlook, entirely different interpretation. Okay? So I can't say, and this is something that is actually dangerous with this particular functional group, and we'll come back to that, which is why I picked it, okay, that this molecule is not acting as an acid and a base in this particular scenario. All we're saying is that it's acting as a base.
Right there.
Okay. Could it also act as an acid? Maybe. We'd have to evaluate that as a separate reaction. Okay, because that's doing two entirely different things. We're looking at my ability to share something, okay, versus my ability to take something.
And it just depends on what it's reacting with?
It very heavily depends on the particular scenario that you drop it into. And yes, that becomes a very important characteristic behind this, and it's something that drives almost everything that we deal with. Okay? So, cool, we've got labels. So if I ask now for you to tell me what species is the acid, what can you tell me? Simplify a little bit. What species is the acid? Silence is a bit of a problem considering we have labels, and therein lies our next issue. That might be why there's silence. You're like, well, you've labeled both of them as acids.
Yeah.
We have two things labeled. Well, which one do you want, Mike? Okay. And I would argue that's confusing, and so what we need to do is clarify that language. And the way we clarify it is the things that are on the right-hand side are not just acids and bases. We call them conjugate acids and bases. So now when I ask what species is the acid, it's HCl. If I ask what species is the conjugate acid, it's that nitrogen structure. And that adds clarity to how we can communicate the knowledge of what's happening within this reaction. Does that make sense? Okay, so cool. We've got full labels now on this. And before we move on to the other scenario, we should add the next layer behind this that we can also now go through and do. We can add.
I have one more question before we.
Okay, fair.
For the conjugate,
I'm actually going to clarify that while you're talking.
because I mean technically it runs both ways. So is it just based on like left to right of like these are your products, these are your reactants?
Yep.
And so your reactants are then going to be the conjugate?
So, and this absolutely becomes a confusion with all equilibrium reactions, is where do we define reactants and products? The hardcore kind of definitive line is products are always,
Reactants are always
yes,
left?
thank you. The reactants are always on the left, your products are always on the right. That does not prevent the products from reacting to make your reactants. Well, that sounds really bass-backwards. Yes, it is, and we don't have language to help clarify that.
But
right.
for like
So
this purpose.
for our purpose, reactants are always on the left, products are always on the right. If we want to talk about the reaction going in reverse, what do we say? Exactly what I just did.
The reverse reaction.
I want to look at the reverse reaction. Okay? So that's now changing the label system, and you just have to recognize to be a little bit more fluid within that system. absolutely confusing, and there isn't much we can do about that. Okay? Back to my question, what's the last thing we can add?
Oh. The type of reaction? But we know because.
We already know it's acid-base.
It's nucleophile or electron.
So as soon as it's nucleophile, electrophile, those by definition do not involve hydrogen. So that's going to open up substitution, addition, elimination.
Radical.
And it actually doesn't include radical, because radical does its own shitstorm of a mass. There it is.
Oh.
Okay, so it's not nucleophiles, electrophiles, because we are by definition transferring hydrogens, which means we aren't going to use those terms, because those terms don't move hydrogens. So what we should be doing is adding curved arrows to explain how the electrons moved in the course of this reaction. That is a challenging concept, because when we look at this reaction, well, the atom moved. Atoms always move. Okay? If proximity is what created a product, we'd have a lot of problems. Okay? Think to world populations. Okay? Just putting a male next to a female, if that produced a baby, we'd have a lot of issues. It's a little bit more than just proximity. Okay? In fact, it's a lot more than just proximity. Okay? So those other things have to be taken into consideration, and ultimately, when we're talking about our chemical reactions, it's how the electrons moved. This is why the Bronsted-Lowry definition isn't particularly good, because it doesn't look at electrons, it looks at atom motion. Okay? We can fix that because we already know how to show how electrons move. That was our curved arrows that we used with, heaven forbid, resonance. So now we have to go back and use those same curved arrows to explain how this reaction happened. Okay, so what do you see?
Hydrogen with the chlorine.
Yep,
That bond between them.
yep.
You're going to draw an arrow from that bond, and you're going to draw it over to the nitrogen lone pair. Or is that too far? You need to just draw it.
Okay, so there's a good question. Is that too far? Okay, proximity is all relative. When we look at our drawings for where things are, your arrow is as long as is absolutely necessary according to how you drew it. Your drawing is entirely arbitrary. You should have maybe redrawn them closer, so you use shorter arrows. Because you don't necessarily know how a reaction is going to run, your arrows can be wicked long. The length of an arrow is 100% irrelevant.
Okay. And then you're going to draw...
Let's pause.
Oh, wait. Sorry. You're going to
No,
draw...
pause.
No, you're going to
No,
draw...
no,
It's
no,
not
no,
from the
no,
bond.
no.
I got excited.
I know. Okay. I dropped a long pause in here because I wanted people to stare at this and look at it and really think about it. Sydney now seems to want to add something else and doesn't like her answer. That's what it sounds like.
I just need you to change it up.
I know.
just a
No,
little
I'm
bit.
not changing it a little bit until somebody else tells me what's wrong with it.
Drawing out.
What do you mean? I don't know what that means.
Wouldn't you draw the arrow going on to the chlorine?
Why? Which is what I think you're suggesting too.
Because that happens first, I guess. Or because electrons can't move that far, or
Nope.
they can't move to a different structure.
Nope.
No.
What happened to the chlorine? Look at the chlorine here, look at the chlorine there. What happened? And? Where did that lone pair come from? And what charge was the hydrogen when it was lost?
Positive.
A positive. What is this arrow trying to show the motion of? That gets real hard to answer that question.
Movement of a bond, or I guess electron.
Right. So let's try it this way. Let's draw what this arrow means. Right. And this is going to get a bit wonky. Okay. The chlorine in those lone pairs are still there, right? Yes. What happened to the electrons in that bond?
Sharing,
They're sharing between what?
hydrogen, chlorine.
What does this arrow mean? The bond, yes, means we're sharing electrons between the hydrogen and the chlorine, but what is the arrow saying we're doing?
Take it out.
We're taking those electrons and we're doing what with them?
Electron.
Where are we moving them?
To
To
nitrogen.
the nitrogen. Okay. We didn't do anything with the lone pair on that nitrogen. It's still there. So now we have that line representing our curved arrow. What's it connected to?
Hydrogen.
I would agree. Absolutely. The hydrogen. What that arrow showed the motion of was an atom. Atoms don't move. Electrons move. Your arrow moves the electrons. And if you're going to say, I'm going to take these electrons and move them over here, that means this nitrogen now has access to them. And then you decided to share it with hydrogen. I'm okay with that. That's fine. What's the problem with this drawing? You've exceeded the octet like crazy. What's the problem with the chlorine? It's missing its octet. This is one of the reasons why we can draw the products. If we follow the definitions, we know what our structures are supposed to look like, and we can backtrack what the arrows are supposed to do. Okay. Now, Sydney, you want to surprise me with a different explanation of what your arrow should be?
Well, so I jumped the gun. So the bond, that arrow is going to be pointed to the chlorine, and then the hydrogen, you can draw a little arrow above that, and then you can put it to the nitrogen.
What do arrows show the motion of?
You're moving electrons.
Does the hydrogen have any electrons?
No.
So I love your first arrow. The bond goes to the chlorine.
But
Yes.
You still have to show that the hydrogen is going to go over to the nitrogen?
No, you don't show the motion of atoms. What do you show the motion of? Step away from bonds.
Electrons.
Electrons. Where are the electrons?
There's no electrons.
It's not true.
Oh, they're the lone pair on the nitrogen. So it would be wrong if you draw the hydrogen?
Yes.
That's...
Because what you're moving is an atom. You can't move atoms.
Okay.
Okay? And again, the proximity thing is probably the best example I can suggest. Okay? If we think about how we reproduce as humans to make new products, to make little babies, Annie's going to be really freaked out right now. Okay? Make it worse than stand next to Kimball. How is that happening? Proximity does not cause the formation of a baby. Proximity does not cause the formation or breakage of bonds. It's the transfer of the electrons that cause it. Okay? Because when we look at a reaction, these things are hitting each other. Okay? All the time. I can take a pen and a cap and I can smash them together and they don't form a connection. I can do this. They don't form a connection. Proximity-wise, they are right next to each other. Why are they not making a connection? The orientation wasn't right, right? Okay? But now if I change the orientation and I try to make a connection, it still doesn't work. Right? I made a connection, didn't I? But it falls right apart. What happened there?
Same force.
there wasn't enough force to cause the connection to change. So when we're talking about chemical reactions, there's this hidden thing that's happening on the background, okay, that we can't describe particularly well. We can quantify it. We can monetize it is the right word, but I don't know. Monetize is all I got. Monetize it as we're monitoring it. We're monitorizing it. Monitorizing. Let's go with that. We're surveying it. Okay? And we can find ways to say, oh, well, that's why that reaction didn't work, because the orientation was wrong. That's why the reaction didn't work, because they didn't have enough force to come together to make that product. Okay? And then what we can go through and do is try and change things. Okay? Orientation, organic chemists are horrible, clumsy chemists. What we do is we take a bunch of pens without their caps, we put them in a paper bag, and we shake it a whole bunch. Then we spill it out and we go, oh, we didn't shake it enough. We put them all back in and we shake it even harder to give it even more force. Okay? And all we're hoping for is random motion to get enough orientation to, boom, make the connection. Does anybody do it better than organic chemists? Biology. Biology takes two materials, brings them together, boom, makes something. Okay? Why can they do that? Well, they've created these massive enzymes and proteins. And what are those enzymes and proteins doing? They are changing the orientation of those molecules to force that orientation to happen. So they change and eliminate all the incorrect orientations to make the correct orientation. Why don't we do that in organic chemistry? We're trying. Okay? But one of the problems becomes it's uber specific. Okay? Same thing as for biological systems. Okay? They very specifically target one thing. They'll work great on glucose, okay, to break a bond in glucose. But you give them a different structure, try and break that same bond, they fail miserably at it. Why? Because they're grabbing glucose. They're using the rest of the shape of that molecule to force the reaction to happen. Right? So when we go through to try and draw what's going on, we're trying to be very kind of cognizant and careful to eliminate the atom motion, because the atom motion isn't what's causing anything. It's the electron motion that's causing a chemical reaction. Okay? So cool, we've added curved arrows, we've defined acids and bases. Have we defined whether this reaction should go forward, red arrow, or backwards, black arrow? No, we haven't.
You mean like what's favored?
Mm-hmm. So how could we figure it out?
Your pKa's.
We could look up pKa's. And if we go through and look up the pKa for our acids, we'll find the pKa for HCl is -4, I think. Okay? Which is wicked small. And what do we say about pKa's being small? They're stronger acids. HCl is by definition a strong acid. It's negative. It's so small that it immediately goes, boop, get rid of this hydrogen. What happens if we look at the pKa of our other acid? Well, we'd go over to the other side, and it's this guy, and we look up its pKa, and we find its pKa is 9. So now what does that mean?
That acid is stronger than that acid, so then it's going to make more products, so it's favored.
So the red arrow is favored. Okay, that's what that means. Okay, we could try to use charge, size, electronegativity, resonance, and all of that in this explanation, and this one doesn't work. And one of the reasons it doesn't work hinges right here on that HCl. HCl is a strong acid, and it effectively breaks the system. Okay, so we can't use the charge size ranking system because if we look, our reactants are neutral and our products are charged, we would think reactants should be favored. Okay, but HCl being a strong acid, one of the reasons why I think it's really important to have that memorized so that you can predict these pseudo exceptions to the rule. So far, so good? What happens when we move to the bottom? Well, we move to the bottom. We're now saying that nitrogen should act as an acid. If it acts as an acid, what should it react with?
Which,
It should react with a base. And a good classic base,
sodium.
sodium hydroxide. Okay. Before we get too excited about trying to predict products at this point, the first thing that I would suggest we look at would be, what do we know about sodium hydroxide?
Strong base.
It is a strong base, but it's a little bit different than our HCl. What kind of bond did we have in HCl?
Covalent.
Polar covalent. Polar covalent bond. What kind of bond do we have sitting in sodium hydroxide? Ionic. And as soon as we see that ionic bond, we should immediately address that and fix it. And the way we fix that is acknowledging that the sodium is going to spin off as Na plus and become a spectator ion, and our hydroxide will sit there as OH minus. Okay? So now what happens? So now we get some choices. In the previous example, the previous reaction, we went through and said, we know the nitrogen's acting as a base, or actually we said the HCl, we knew that one was acting as an acid, which means it had to donate a hydrogen, which means it had to be Cl minus eventually. Okay? So we use the definitions to predict our products. What do you guys think? Do you want to use definitions again, or do you want to try and use the curved arrows to predict our products? You will ultimately be responsible for both, so getting practice in both is useful, but since you have two tactics, whichever one's more comfortable, you can use to help guide you for the other. Do you want arrows, or do you want definitions?
Definitions.
Definitions, okay. Which definition do you want to look at, the base or the acid?
So acid by definition has to donate a hydrogen, so it's going to donate one of its hydrogens.
Okay. So I'm going to delete one of those hydrogens.
So the nitrogen will take the lone pair from the hydrogen bond that it was bonded to,
Cool.
and then the oxygen is going to take that hydrogen because it's electronegative and negative, and hydrogen's positive.
Remove electronegativity from that argument.
Okay.
You don't need that at all. The oxygen was negative, and if we finished out its Lewis structure, it has 3 lone pairs. So what can it do? It can share one of those lone pairs with the positive hydrogen,
And it becomes
making that new bond,
H2O.
making it become H2O.
And then sodium is just kind of like out there by itself.
And the sodium still spectates, gets to watch everything. We predicted our products?
Then you label them?
Not yet.
The chalk.
Oh, charge, yeah.
What happened to the nitrogen?
Becomes negative.
It is negatively charged.
Yeah.
What happened to the oxygen?
Positive.
It stays negative because it's not gaining electrons.
And this becomes the fun one to try and figure this out. Okay, it didn't gain electrons, so it shouldn't become more negative. Did it lose electrons?
It's sharing them.
So if I have my iPad and pen, right, and I share it with somebody else, is the iPad and pen as close to me anymore? No, I've lost a little bit of control over it.
So it becomes positive?
Right? Does it become positive? So yes, it's lost some electrons, but it started negative. If something starts negative and loses a negative, it becomes neutral.
Oh, yeah.
No charge. Okay? So, and I love how you guys walked through that. Okay? That's fantastic. I just want to caution you, that's insanely slow. right? And this is where falling back on a new system and being like, oh, it's new, I don't know, think through it, okay. Is water a new molecule to you? What's the charge on water? It's neutral. Okay? So don't let what you already know disappear from your knowledge bank. Okay? And I fully acknowledge that we're doing some crazy stuff. It's easy to get lost in those other details. Okay? But that oxygen is absolutely neutral. Okay? So now we could go through and do the labeling system. Okay? I'll give you a start. These are conjugates on our product side. We'll call it the nitrogen compound and the oxygen compound. Acids or bases? One thing that can help for the water to go back to the reactant, what has to happen to its structure?
It's gotta lose its hydrogen, but since it's technically water, can that be your acid? Oh.
Yeah. This is one of the reasons why water is very special. Water can act as both an acid and as a base.
Just because it can donate.
It can donate hydrogens and it can accept hydrogens. So it is absolutely donating a hydrogen, which then means the other one must be a base. What happened to its structure?
It lost a hydrogen.
Did it lose a hydrogen? Okay. And you guys are looking at it backwards. Okay? And by backwards, you're looking at it forwards. You need to look at it backwards. What happens when we go from this negative nitrogen to that nitrogen? It gains a hydrogen.
Accepts one.
It accepts a hydrogen, which means it is
A base.
a base. So our definitions are correct. Okay, and I'm going to carefully try and erase this purple arrow, which is probably not going to work very well, but I'm going to try. Okay, what's the last thing? Or two, there's several things that we have left that we could look at.
pKa's.
Yep.
Arrows,
pKa's, arrows, and then we could also bring in, can we use that ranking system that I talk about for looking at stability for reactions? And yes, we can. So if we look at pKa's,
Is it water like 15?
cool, so we know the water pKa, we've got that one memorized. It's about 15, 16, as long as you're in that ballpark. What's the pKa for this one? That's the other acid. I like where you just looked. Yeah, where are you looking? You're looking up here, right?
That's not it.
Is this molecule the same as this molecule?
No.
No, which means it's not the same pKa.
Where did the pKa go for the? Oh, we only do it for acid.
We only do it for acids. What does the A stand for in pKa?
Acid.
Acid. We only care about the acids. That button's not buttoned. For the record, on my shirt, since that could be really weird in the video. Did you memorize it? Probably not, because it's a confusing one. And looking it up, I'm going to bet if you look up the pKa for an amine, they're going to tell you 9. Which is really rude, because that's not what they're talking about.
9 to 10.
Yeah. And what are they talking about? They're talking about this one. Why? Because when we look at amines and we think about their reactivity, where do they show up? Where do amines show up? Anybody know?
In, like, acids?
Well, there's an interesting word. Have we ever heard of amines and acids showing up in the same place?
Yeah.
Amino acids. So when we're looking at biochemistry, and we now shift to the biology side of it, okay, we will only focus on pKa's that are relevant to biochem. And in biochem, we're only in water, which means the pKa range that we're dealing with is usually 0 to 15 capped with water. That's it. That's all we can deal with. Which means when we look up the amine functional group, The only pKa that's relevant to us is the one that falls in that range, which happens to be for the ammonium version of it. So when someone looks up an amine pKa, what they're referencing is not the acid form, they're referencing the conjugate acid form, which is insanely frustrating. Right? So what is the pKa for an actual amine? Yeah. And that's why in the notes I write it as 9/35, because depending on what level you're looking at, you'll see it referenced differently. If we're looking at an amine, its pKa is 35. Absolutely, hands down, 100%, that's what it is. When you move into biochemistry, they will reference the amine as having a pKa of 9. It is not the amine that has a pKa of 9. It's the ammonium salts, the ammonium conjugate acid of the amine. Shut up, all the devices. They're all mine for the record. Okay? So what does that mean for this reaction? It favors the reactants. And if we think back to the initial question, how do we decide whether something acts as an acid or a base? If you don't know, you could draw the reactions and evaluate the pKa's. The pKa's would help you process and figure that out. Okay? But did we have the pKa's memorized? No.
Partially.
Okay. We had them partially memorized. Okay? And therein lies the big problem with our amines as functional groups. Okay? And they'll continue to kind of haunt us. They'll haunt you more because you have to deal with biochem if you're taking biochem. Okay? We would like another system that would allow us to predict these reactions without having to look up pKa's. Okay? And that's that reactivity video that we talked about, right? That I made you watch. And in that reactivity video, I'm going to delete the acid-base stuff up in the upper left-hand corner. I say what you need to go through and evaluate is charge, size, that's a Z, wow, that was a horrible Z. Electronegativity, which I'm going to use the chi symbol for, I believe we've talked about that. Resonance, induction, and then on a rare occurrence, we'd move into O, and I'll talk about where that O comes from, but for me, I've always referenced it as O carp, because I can't swear. Don't go back and quote me as being wrong in all my videos. And when we go through and evaluate these, the charge, size, and electronegativity are all atomic effects. Resonance induction are molecule effects. And then that last one is an everything effect. I would give it that O again. What this is kind of a hat tip to is a mnemonic device that I don't know who created it. I know a very smart person at ASU used it. They reference it as Cario. Okay? And I object to it because the letters don't align. Like they just don't make sense to me. Okay? And I think it negates some of it. But C for charge, A stands for atomic effects. Well, which atomic effect? The size or electronegativity? And which one should you look at first? Well, you look at size first. If you just have it as A, we don't know. R is resonance, I is induction. O, I have never been able to get a straight answer for, which is why I turned it into O carp, because there's a whole bunch of different things that actually fall in that category. And in fact, we use that category to explain the difference between a trans versus cis double bond. We use that category to explain the difference between tertiary versus secondary carbocations. Okay? You're looking at very nuanced kind of small effects, not these larger picture kind of things. Right? I believe the official definition is orbitals. And if you're like, I don't know what that means, I don't know how that would apply either. Right? So can we use that one down here? Well, yeah. Okay? And one of the things that we want to start with is try and find charge, because charge is a big red flag that something is crazy and gnarly. So we can look at our reactants. Well, the acid isn't charged, but the base is. Okay? So I'm going to look there. That's a good focal point. I'm going to look at that guy. Now I'm going to go through and look at my products. Well, the nitrogen is charged, so I want to look at that. And then the water's not charged. Right? And so what I want to do is compare now my reactants to products to say which one is more stable. Well, charged. They're both charged. So I don't see a difference. So now what do I move to? Well, size. So I look at the atom, because it's an atomic effect. The atom that makes this unstable is the oxygen, because it's the one that's negative. The atom that makes this one unstable is the nitrogen. Okay? So size. Is there a size difference between oxygen and nitrogen? And that's a harder question to answer, and his confidence in that makes me happy. Okay? This is one of the very first things I told you you needed to know. Okay, was the trends in size. And in particular, across a row, there's a negligible difference in size. Since oxygen and nitrogen are in the same row, size is irrelevant to us. So then what do we move next to? Electronegativity. Is there an electronegativity difference between oxygen and nitrogen?
Yes.
Yeah. Okay. What's that difference?
Oxygen is more electronegative.
More electronegative. What does that mean about the charge on oxygen versus nitrogen?
Oxygen is going to be, it wants to steal more than nitrogen does.
Which means oxygen as a negative is more stable than the nitrogen. Which way should the reaction favor? It should favor the negative oxygen. And we get a direct backup of the pKa information. That's pretty gnarly. Okay? So I don't have to memorize pKa's if I know the order in which I should be evaluating how that charge can affect stability within a molecule. That's pretty impressive. And what we'll find is that that ranking system works in the vast majority of cases. Right? 90% might be a bit high, but it's pretty dang close. Right? There are problems where it fails. Usually where it fails are around strong acids. Strong acids break that ranking system. So if we look at our initial reaction, the reactants are uncharged, but the products are charged. Right? So according to our system, it should favor the reactants because the reactants aren't charged. Right? That's not true. It definitely favors the products. Right? And why? I think it really does sit on our strong acids being the breaker of that system. Kind of, sort of? Does that make you feel better or worse? Lindsay, since you started that, I'm going to blame you for it.
It makes you feel a little better.
Just not a lot better.
Not quite understanding where we're getting the pK values from, I guess.
So, and yeah, because when we talk about those pKa values, it seems like I'm just pulling them out of thin air.
Yeah.
I'm not pulling them out of thin air. I have them memorized.
Okay.
Okay? And so therein lies the issue. When did I memorize them? I've been doing this for 20 years, 24 years-ish. Okay? I've probably memorized those pKa's within the last 10 of those 24 years. Okay? So what does that then mean to you? That's where I would go with it. It means you don't need to memorize it. Okay? Does that mean there will be cases where you will be wrong? Possibly. Okay? That is quite possible. Okay? But those are going to be small numerical cases. Okay? So points-wise, meh. I would accept that as a loss. And I would push towards, do I understand what's happening within it to be able to figure that out? That's why I don't want you looking at pKa's officially. It absolutely can help, but you have to have a lot memorized to be able to nail that down. And is it always going to support you? It won't. Okay? It works great when we talk about acid-base reactions. We're halfway through the semester, and I just said the other half of the semester is not acid-base reactions. So how would you predict reactions then? Charge, size, electronegativity, resonance, induction. Okay? Because it works there as well as acids and bases. That's why that mechanism or that process is lovely, because it's universally applicable. Whereas pKa is really only applicable to acids and bases. Okay? It's powerful, absolutely. But its applicability is very, very narrow. So maybe feel a little better?
Yes.
Right. Having some memorized, sure. But like spending a lot of effort behind it, I wouldn't bother. To me, drawing out quick structures, I could probably do pretty quickly. So if you've been getting used to drawing structures, what you might go through and do, can I delete everything? What you might do when you get the test, come on, where's my screen? Is do something like this. Right? There's not labels on those, but what am I trying to identify? pKa. Okay? So I'm trying to, as quickly as possible, drop those pKa values so I don't have to have them memorized for the whole test. I just have to have them memorized for the 30 seconds between when I say put your stuff away to when I give you the test. Okay? I have no objections to you word vomiting stuff onto your test. Word vomit, not actual, please. That's absolutely fair.
Would you say it'd be just those 4 that I would most likely benefit from?
Those are the ones that
memorizing?
stand out to me. I'll officially add that would be the last one I would add. I happen to know or think I know that this one's about a 40. And this one's sitting at 50 to 60. Because those are the big primary functional groups that we'll end up seeing. Okay? And even then, we'll talk about other ones as the semester goes. In fact, this one is the bane of second semester students. If you're like, oh, dang, second semester, I don't have to worry about that. This is supposed to be a survey course that covers the entire year. So yeah, you'll have to worry about this one. That one sits about 16. Okay. Which is gross because that's a hydrogen bonded to a carbon. You'd be like, well, shouldn't that be up in the 20s, 50s range? But because it's next to the carbon-oxygen double bond, it changes its pH or its pKa so drastically that it now starts to come in and become biologically relevant. Kind of, sort of. We are officially done, so I should probably stop talking. If you couldn't guess, if you don't stop me.
Could you potentially, is there another class in this room right after this?
I don't believe so.
Could you just go through like a different example, going through the 1 through 6? The charge size, like establishing it that way, I mean.
Whoop, that's not what I meant to push.
So substitution, elimination, addition, none of that's gonna be on this exam?
So, yes and no. So I didn't stop the recording. So what we just went through and did with acid and bases is you're fully responsible for all aspects of acids and bases. Substitution, elimination, addition, you're not responsible for all aspects. You're responsible for looking at it being like, that's an elimination.
Oh, okay, just identifying it?
I don't know why that should work. I don't know what the components are. But I know that's an elimination.
Okay.
That's what you're responsible for when you look at those reactions. The mechanisms, and this to your question that you, was it an email? Maybe it was your extra credit actually.
Oh, the predicting the nucleophile addition?
Yeah. So, your statement somewhere, again, I don't remember where it was, predicting products, okay? And I think you tied it to like a substitution or elimination reaction. And my response was, no,
Not yet.
not yet, but there's a gray area. And that gray area actually works right here. Should you be able to predict the products? Yes. Okay. I don't even need, with how I'm asking this, okay, what this would come out, this would be more of a short answer, and I would be like, tell me what the products are. I don't care that what reaction type it is. What do I care about? Why am I asking this question?
So to see if we can see where things go and make it correctly,
How do you see where things go?
like how it reacts.
What are you looking at to determine how it reacts?
Electrons.
Dang.
The
Can you just say the word I want you to say?
molecule?
Because no, I don't want you to look at molecules and be like, this is the product. I don't expect you to do that.
But like the interaction between
How is this not,
mechanisms?
how is the mechanism different than everything else? What does the mechanism contain within it that most reactions do not?
Resonance.
It's not resonance. It's the curved arrows used in that are used in resonance. We're using those same curved arrows here. You are given instructions with those curved arrows. Should you know how to move arrows? Yes, that's moving electrons. So that's all that you're saying. You just didn't tell me curved arrows,
Oh.
okay? Because I don't want you looking at just a bunch of structures and be like, oh, it's going to be this product. No, no way. No way in hell do I expect that. And probably at borderline, that might not ever be a question I ask. Because what I want you to be able to do is, do you understand how these things can interact? And let me provide some guidelines on how these things are reacting. That's what the curved arrows are supposed to show. So do I expect you to predict product here? Yeah. Yeah, I do. Okay? Because you have those curved arrows. If we go through and do this first curved arrow, we'll call that one 1, is showing the oxygen sharing electrons with the hydrogen. Which means that pair is now in a bond with that hydrogen. Okay? But that next arrow took those exact same electrons that were holding on to the hydrogen in that space, right? And it said they aren't there anymore. They're where?
On that bond. What's a
Okay?
double bond?
They're in that space between the two atoms, which is a bond, which would be making a pi bond. Whoops, I didn't want that color. I wanted this color. So now I have a pi bond. For the record, that versus this are identical. Don't stress. Okay? Then, arrow 3, what happened?
That bond, it's the electrons are going to the bromine. So it's breaking off.
Do I expect you to be able to predict products? Yes, in this scenario. I'm providing you guidance. Tell me you understand that guidance. That's what I want. Okay? So in that respect, yes, I do expect you to predict products, but there's guidance there. That guidance is something that's challenging to understand. It's in dealing with curved arrows, but I expect you to be able to pull that off. But I would never just say, here's some reactants, tell me what the products are. Okay? And even projecting outwards, I don't know that I would ever ask it as a blanket statement like that. What you would get is, the following shows a substitution reaction, predict the products. So we've narrowed the field a little bit, that it's not just everything, it's this one thing. Can you, within that narrowed field, predict a product to come out of it? Does that make sense? Okay. The other kind of question that I would ask, if we go back, is given, and I mean, all that stuff there, it becomes obvious what the answer would be. But I could give you this, and I could say, what reaction was this? okay?
It's a new double
And-
bond.
I love that you're using the term leaving group. Even that officially, I would say we haven't covered in lecture. Lab, yeah. This is our lab lecture dynamic is a little bit out, but it does have a leaving group, yes.
And a double bond.
A new double bond. I mean, I don't know why I had to draw it. It says it, okay? So what reaction produces a double bond?
Elimination.
So you could tell me this is an elimination. Okay. If I had asked that, I probably wouldn't show you the arrows. Okay. You should still be able to tell me it's an elimination. I see a new pi bond. Okay. Yeah, that's an elimination. Giant red flag. Okay. So that's fair. I could also, whoops, don't erase everything. Say, what mechanism is this? Okay. Because you've identified it's an elimination reaction, you should also be now thinking in the elimination mechanisms. Okay. And that does get harder because you have more mechanisms to deal with, but that's what that mechanism video was about, is trying to break down the pieces within it. Okay. So should it be an elimination mechanism? Well, do you produce a new pi bond in this mechanism? Yes. So it should be one of the elimination mechanisms. There's a couple different types. Okay. Within those different types, you have electrophile elimination and you have nucleophile elimination. Okay. So in the formation of this pi bond, what did you eliminate from the molecule?
The leaving group.
What charge was the leaving group? And this becomes very important.
It's negative now? Or wait, sorry, what are you asking?
Yeah, it would be negative. Yeah, this one actually gets a bit complicated. You've got that negative, and you also removed that hydrogen, which was positive. So you did both of these things at the exact same time, right? Okay. So you can't really call it an electrophile elimination because you eliminated a positive thing. So electrophiles are positive, nucleophiles are negative. We eliminated a positive hydrogen, and we eliminated a negative bromine. That hydrogen is kind of an electrophile according to this, albeit weird definition. The bromide is a nucleophile. So which one did you do?
Both.
Both. Well, if we did both simultaneously, shouldn't we have a different name?
Yeah, isn't that SN1?
S stands for,
Oh, substitution.
so it can't be S. What is it?
EN1.
Right.
EN2.
Okay, E2.
E2.
Okay, because we're doing two things at the same time. You're getting rid of an electrophile and a nucleophile. Okay, we could look at it that way.
Wait, where's the N come in?
The N comes in from how that reaction is happening. SN, substitution using a nucleophile.
Oh, yeah.
Are you using a nucleophile in elimination? No, it's what's left over that we're actually using to define that last piece. So this becomes an E2 mechanism.
Because there's two steps happening at once.
I accept that. Two steps at once. The at once becomes the critical part of that.
Simultaneously.
Yep. Okay. Is that part harder? Do you find this material more difficult than all the other stuff we've looked at?
Not necessarily.
Okay, I mean, that's fair. So, and if everybody else is like, oh, she's fucking lying, man, this shit's hard, then spend your time elsewhere. The whole test isn't this. That was what we broke down at the beginning, right? We've got all of those components. This mechanistic stuff is the very last kind of part of it. We've got lots of other pieces. Will you still see questions on this? Absolutely. This is the rest of our semester, is looking at pretty much each of these in detail. Saying, well, here's a new system, here's a new system, here's a new system. Okay, and ultimately there, it's here's a new structure, a new functional group, this is how it can react. Here's a new functional group, this is how it can react. And we start to nitpick all those details. Some of those details being leaving groups, substrates, nucleophiles, okay, bases. We start really drilling into those, okay? That's now getting into the weeds of the class.
But this, for example, like you wouldn't be like, tell me what, like stating that it's an E2, that's not gonna be on this exam.
That's all, that, with this context, yes. That's what we just walked through, yes. Okay, being able to recognize those. I do absolutely think that's challenging. Okay, the exam is next Wednesday, not this Wednesday, but next Wednesday. You have time to practice those things. Okay, that's one of last class. That's where I said what I want to do is just open up this named reaction things and be like, poof, here's a mechanism. What kind of mechanism happened? And just look at it. And it's just looking at examples and saying, what are the pieces? How did this break down? And then matching them back to those scales. The matching them back, unfortunately, isn't super clear here. But that's all of your mechanistic steps. Okay, so there's 1, 2, there's 6, 9. There's 6 mechanistic steps. And there's some overlap, because you see addition, you see elimination, you see S for substitution, you see AB for acid-base. So if you know those reaction types, that can help limit and kind of categorize these sections. The individual examples, that's what each of the rest of the slides are, okay? Are looking at specific examples of what's happening that represent those mechanistic steps, okay? So that you can see those pieces. Okay? Kind of, sort of? Okay, I just need to stop this recording.